This is lesson 6.2, the kernel and range of a linear transformation. Now, I think as long as that title already is, we could add a lot more to that because those are not the only two things we're going to talk about in this lesson. There's quite a number of other things. In fact, as you can tell by the timestamp, this is a rather lengthy lesson. So just ask that you hang in there, and we're gonna do our best to really make sense of all of this and do so in as timely a manner as possible. So we're going to start right off with the definition of a kernel of a linear transformation. It says, let T be the linear transformation such that V maps to W. Then the set of all vectors V and V satisfy T of V equals 0 is the kernel of T and is denoted by KER, kernel T. All right, so notice the kernel, all the kernel is just the set of all vectors. It's a subset of all vectors in V that, when we apply the transformation, maps to the 0 vector in W. That's all it is. So it's a subset in V containing all the vectors that map to 0 in W. So example 1 says find the kernel of the linear transformation from R2 to R3 represented by tx1 x2 equals x1 minus 2x 0 and negative x1 equals 0, 0, 0. So technically the equals 0, 0, 0 isn't there. I just added that in just to remind us that what we're really doing is asking, when does this rule map to 0, 0, 0? So we're going to take x1 minus 2x2. We're going to set that equal to 0. Obviously, 0 just equals 0 for the next one, and then negative x1 equals 0. So in this case, what happens is, obviously, x1 is 0. And if x1 is 0, going up to the first equation, x2 must also be 0. So in this case, the only vector that actually maps to 0 in W is the vector 0, 0. So our kernel of T then in this case is the vector 0, 0. And again, it's a subset. It is a set, so we're going to put that in set notation. All right, so that's a pretty straightforward one, just a real quick example just to show you what a kernel is. Let's do one that's a little more involved. So we're going to again find the kernel, this time of the linear transformation mapping R3 to R2, defined by T of x equals A times x, where A is the matrix 1, negative 2, negative 1, 2, 3. All right, so again, in this case, what we're looking for is we're mapping from 3 to 2, so we're looking for all of the vectors that map this to the 0 vector in W. So if we think about mathematically what's happening here, we're going to take this matrix, and we're multiplying this matrix by a 3 space, right? We're in the 3 space right now, so we'll just use x1, x2, x3. And what we get is something in the 2 space. So in this case, we're going to get a 2 by 1 matrix, and it's the 0 matrix, right? Because again, kernel maps to the 0 vector in W. So in this case then, what we're going to do is just reset this up more in that form of an augmented matrix. So 1, negative 2, 0, and negative 1, 2, 3, 0. And we're just going to simply use reduced row, or put it into reduced row echelon form, and then use that to find the kernel. So in this case, if we do that, if we apply the Gauss-Jordan elimination method, this would give you 1, 0, negative 1, 0. And obviously you can use technology to do this if you'd like, or do it by hand, either one. And so what that gives us then is x1 minus x3 equals 0, and x2 plus x3 equals 0. So those are the equations that we get out of that reduced row echelon form. And so now, thinking about this, basically then x1, if I put this in a different form, don't know what's going on up on that corner of the screen. We're just going to ignore that. Basically, what we get is x1 equals x3, and x2 equals negative x3. So if I let x3 be t, I'm going to put this into matrix form. So if I let x3 be t, then x2 is going to be negative t, and x1 is going to be t. Or another way to think of this is t times the matrix 1, negative 1, 1. And so our kernel in this case, the kernel of t, is going to be just this vector, this 1, negative 1, 1 times t. So I'm going to write it like this, t times 1, negative 1, 1, where t is any real number. Think of t basically as a scalar. Okay, so it's just in the real number set. Sometimes you'll see, instead of writing it in this form, we'll just talk about the kernel as a spanning set. So sometimes you'll see this also written like this, where it's just the span of the vector 1, negative 1, 1. So either one, you write it either way, but I just want you to be aware, because if you're doing a problem, checking in the back of the book, or maybe you're finding problems online and doing those, you may find the answer written in different ways depending on the source. So that is the kernel. Kernel, again, is just the subspace in V that maps to the zero vector in W. All right, so next one is then the theorem from that, and it's what I've just mentioned. It's that the kernel is a subspace of the domain of V. The corollary says that if we map Rn to Rm, given that t of x equals a times x, then the kernel of t is equal to the solution space of a times x equals 0. So kind of similar to what we just did, we're going to do the same thing here. We're going to take our matrix here. We're mapping R5 to R4. And we've got the matrix A. We're going to find the basis for the kernel of T as a subspace of R5. All right, so same idea that we kind of just did. What we're going to do is we're going to put this into reduced row echelon form. So I'm going to take that matrix above, apply Gauss-Jordan, again, using technology to do this. And what we end up with is the vector 1, 0, 2, 0, negative 1, 0. And again, let me leave the 0 off for a minute. I'll put those on in a minute. So basically, this is a 4 by 5. So it's 1, 0, 2, 0, negative 1, 0, 1, negative 1, 0, negative 2, 0, 0, 0, 1, 4. And then the last row ends up being all zeros. Now, I started to write zeros before because remember that in essence what we're doing is we're setting this equal to 0. So technically we could write a column of zeros just to remind ourselves that those first 5 columns represent kind of the left hand of the equation, and the zeros representing the right hand of the equation. So again, writing this out now, this is going to give us the equations. The first one is going to be x1 plus 2x3 minus x5 equals 0. The next one will give us x2 minus x3 minus 2x5 equals 0. And then we're going to have x4 plus 4x5 equals 0. And then the last row is all zeros, so we can just ignore that one. So in this case, we've got the 3x5s, we've got 2x3s. So let's solve this for x1, x2, and x4. And let's write this x1 equals negative 2x3 plus x5. x2 equals x3 plus 2x5. And x4 equals 4x5. So again, x then is going to be just x1, x2, x3, x4, x5, x3, x4, x5, which in this case, I'm going to let x3 be s, and x5, we'll let that be t. So then what happens is x1 is going to be negative 2s plus t. X2 is going to be s plus 2t. And x4 is negative 4t. Or if we put this in kind of a linear combination, we've got s times negative 2, 1, 1, 0, 0, plus t times 1, 2, 0, negative 4, 1. So in this case, then, that's our basis. Those two column vectors represent our basis. So our basis for the kernel of t is given by, we'll just call this b equals negative 2, 1, 1, 0, 0, and 1, 2, 0, negative 4, 1. All right. So very, very similar idea. So when you're trying to find the kernel, basically you're getting the matrix into reduced row echelon form. You're setting up those equations based on that form, and then just using the s's and t's as appropriate to then put it into these column matrices, which then represent your basis. All right, well, let's move on and let's talk about range. So again, I guess I'll read through the reminder, or the theorem, and then we'll go through kind of a reminder here. But basically this says that the range of a linear transformation T mapping V to W is a subspace of W denoted range of T. So again, if you remember from our last lesson, we talked about the fact that that when we map from like V to W, right? So here's V, here's W, and we've got our vector V, and we're mapping that into W. Remember that V is the domain, W is the codomain, because not all of the vectors in W get mapped to. They're not all images of vectors in V. So there's this subset where those vectors lie, right? So in that subset, you have a vector W, and that's what's getting mapped to. But there's all these other vectors that may not be images at all. So in this case, then the range is referring to that subspace within W, okay? And so the corollary to this is that if our linear transformation maps Rn to Rm, given by T of x equals A times x, then the column space of A is equal to the range of T. Okay, so if we want to find the range of T, what we're really doing is finding the column space of A. So let's go ahead and take a look at an example of what that looks like. So it says for the linear transformation R5 to R4, we're going to use the same matrix we used from the previous example. Find a basis for the range of T. So again, what we're going to do here is we're going to start by finding the reduced row echelon form, which we already know. We did that in the previous example. So using the Gauss-Jordan elimination, using technology, we get the matrix 1, 0, 2, 0, 1, or negative 1, excuse me. And this time we don't need that 0 column. We're not setting this equal to 0. Again, we're just finding the column space, so we can ignore that the 0 column. 0, 1, negative 1, 0, negative 2, 0, 0, 0, 1, 4. And then again, that last row is all zeros. So that is our reduced row echelon form. So in this case, then, what we're looking for, column space, remember, is if you look at all of the rows and find the leading ones in each of the rows, those rows, or excuse me, those columns where those ones are located correspond back to the original matrix, and those are the columns that give us the column space. So in this case, then, those three columns make up our basis for the range of T. So our basis for the range of T is given by, and I'm going to use B again here, the set, what do we have here? 1, 2, negative 1, 0. Almost use the reduced form. Make sure you go back to the original and not the reduced form. The next one is going to be 2, 1, 0, 0. And then 1, 1, 0, 2. One thing I will note is again, if you're doing problems in the book, if you're finding problems online and you're looking at answers to those problems, it's possible that your vectors in your basis are not going to look the same as the other person's vectors. It's possible that they have taken those vectors, and in this case, these three vectors, and reduced them further, which you can do. Obviously, any linear combination would still work. So if you don't see your vectors in the answers in the same way, don't be entirely alarmed. It's possible that you are correct. In fact, I'm going to say it's likely you're correct. And they're just giving the solution in a slightly different reduced format. So just be aware of that. All right. So this leads us now into rank and nullity of a linear transformation. So we've talked about the kernel, we've talked about the range, and now we're going to talk about rank and nullity. It says, again, let V or T be a linear transformation mapping V to W. The dimension of the kernel T is called the nullity and is denoted by nullity of T. The dimension of the range is called the rank of T, denoted rank of T. Okay. So in other words, so dimension of the kernel is the nullity, and the dimension of the range is the rank. So rank and nullity, we've actually seen these words before. They're just scalars. They're just numbers, right? It's telling us what the dimension of these two things are. So our theorem says that, again, if we've got a linear transformation mapping V to W from an n-dimensional vector space V into a vector space W, then the sum of the dimensions of the range and kernel is equal to the dimension of the domain. Sorry, I'm missing a word there. That is, the rank of T plus the nullity of T equals n, or the dimension of the range plus the dimension of the kernel equals the dimension of the range. Hang on to these formulas. These are going to be helpful to you as you're doing certain problems. So basically the rank of T, which again, rank is just the dimension of range, which we see over here. So rank of T is dimension of the range, plus the nullity of T, nullity being the dimension of the kernel, is equal to n, which is the dimension of the domain. N, again, being the number of columns in your matrix, the dimension of the domain being the number of columns in your matrix. Remember, we map from the columns, number of columns, to the number of rows. Okay? All right, so let's do an example and talk about that. And so in this case, we've got find the rank and nullity of the linear transformation R3 to R3 defined by the matrix. Okay, so notice that this is already in reduced row echelon form. So again, all we're looking for then is we're looking for rank. Rank is the dimension of the range, okay? Range being the leading numbers of ones, or the rows with leading ones. So in this case, we've got a row here with a leading one. We've got a row here with a leading one. So our rank is 2. All right, so I'm just going to remind you in parentheses, the quick, easy way to find this is just find the leading number of ones in those rows, and that's going to determine your rank. And then our nullity is the basically the columns then that with a leading one, right? So nullity was the dimension of the kernel, and so in this case our nullity is going to be 1. And again, that's the columns without. I think I said with before. I apologize. It's columns without leading ones. All right. The other way to find nullity, you could do the formula, right? So we've got the rank equals the nullity, or the rank plus the nullity equals n. So we could find the nullity by taking n minus the rank. In this case, n being the 3 columns, minus the rank, which was 2. So 3 minus 2 would give us a nullity of 1. All right? Okay, so that's kind of about 2/3 to 3/4 of this lesson. The last part is going to go fairly quickly, but basically this whole idea about kernel, range, nullity, and rank all kind of working together, right? They all kind of fit together. Now we're going to move on to what may seem a little disjointed, but definitely ties right back into those ideas. And that is this idea of one-to-one linear transformations and onto transformations. You might remember these words or this terminology from, even back in your high school days, probably like Algebra 2, probably Algebra 2. One-to-one and onto, you would have talked about those in the context of functions. The same thing applies here. So if you can remember what those words mean already, you know what it's going to mean here. So one-to-one just simply means that when the preimage of every w in the range consists of a single vector. Okay, so we're mapping v to w, and it's one-to-one when the preimage of every w in the range consists of a single vector. In other words, t is one-to-one if and only if for all u and v in v, the transformation of u equals the transformation of v if u equals v. So let me kind of do this. So basically, if you remember, and we haven't talked about this actually, but if you remember in functions, let's go back even a step further. In order to be a function, remember functions have to follow a special rule that says if I have an element in the domain and I'm mapping to the range, that element can only map to a single value in the range, right? I can't have this element in the domain mapping to more than one element in the range. If you think about it graphically, and you might remember the vertical line test, if you draw a vertical line through a graph and it hits the graph more than once, it's not a function because it means that one x value is mapping to more than one y value. Okay? So to be a function, this has to be true. Now, you can have two different numbers in your domain or values in your domain mapping to the same value in the range. That's okay, and it's still a function. So what one-to-one says is now you can't have that. So one-to-one says, okay, your function, so that value in the domain can only map to one value in the range. If I pick a different value in the domain, that value to be one-to-one, that value cannot map to that same point. That value has to find a different point to map to. So kind of in the vocabulary of what we're talking about here, every preimage is going to map to a unique image. Okay? No two preimages will map to the same image, is basically what this is saying. The theorem here then is let, again, t be a linear transformation. Then t is one-to-one if and only if the kernel of t equals the set of zero vectors, or the zero vector set. So in other words, this is our test, or this is how we show that a transformation is one-to-one. Okay? All right, so let's go ahead and take a look at an example of that. Well, actually, there's not really anything to do on this one. This is just kind of saying that if you map mn to mnm, represented by t of a equals a transpose, this is one-to-one because its kernel consists of only the m by n zero matrix. Okay, what this is saying is I'm mapping from V of a matrix, a vector, into W, finding its transpose. So mapping a matrix to its transpose. Well, if you think about it, so if I'm doing this, it's one-to-one only if the kernel of T is zero. Well, the only way to map to the zero vector is mapping, or to a zero matrix is to map a zero matrix. So if I'm finding its transpose, the only way to get a transpose that is all zeros is if the original matrix is all zeros. So in that sense then, our kernel of T is zero, and this is a one-to-one transformation. On the flip side, if I perform a zero transformation, mapping R3 to R3, this is not one-to-one because the kernel is all of R3. What a zero transformation is saying is if I take 0 of V equals 0. In other words, V can be anything I want it to be. I'm multiplying it by 0. Of course, I'm going to get a zero vector. So V can be any vector. So basically what this is saying is every single vector in V is mapping to the zero vector, which clearly then would not be one-to-one. All right. So that's how we check. We just basically check to see if that kernel of t is 0 or not. All right, then the other part of this is the onto. So 1-to-1, no two preimages map to the same image. Onto goes on to say then that a function t mapping v to w is onto when every element in w has a preimage in v. Okay. In other words, t is onto when w is equal to the range of t. So let's go back to that idea again that we were talking about before. So in this case, we talked about having that subset where, again, I pick a preimage in v, and it's going to map to an element in w, but it's in that subset, that range. In this case, what this is saying is there is no subset, that every single element in w is mapped to. Every single element in w is an image of some vector in v. So then in that case, then we would say it's onto. And here it says that that basically t is onto if and only if the rank of t is equal to the dimension of w. Remember, rank of t is the dimension of the range. So in this case, it's basically saying that if the dimension of the range is the same as the dimension of the entire vector space w. All right. And then finally, it is both 1-to-1 and onto. We'll just read this. So let T be the linear transformation with vector spaces v and w, both of dimension n, so they both have to be the same dimension. Then T is 1-to-1 if and only if it is onto. So if it's onto, it's 1-to-1. If it's 1-to-1, it's onto, assuming that the dimensions are the same. All right, so let's wrap up with this final example. And I really like this example because this is going to really tie everything that we've talked about in this lesson together. We're really going to cover pretty much everything that we've done in this one example. As far as like all the nullities and ranks and dimensions and all those things, we won't go back and do bases or anything like that, but it ties together nicely a lot of these concepts. So it says, consider the linear transformation mapping Rn to Rm represented by t of x equals ax. Find the nullity and rank of t and determine whether t is 1-to-1, onto, or neither. All right, I'm going to tackle this by making a chart and just kind of listing a bunch of information that we've talked about. So we're going to have, we've got 4 things we're looking at. We've got A, B, C, and D. And A is going to be the transformation mapping R3 to R3. B is going to be a transformation mapping R2 to R3, columns to rows. So 2 columns to 3 rows. C is going to be a transformation of 3 to 2. And D is a transformation of 3 to 3. All right. So let's do this. Let's make a kind of a table here with a whole bunch of information. So I'm going to do the dimension of V. So I'm going to think of Rn as being V mapping to Rm as W, just for kind of ease of identifying and talking about things. So I'm going to find the dimension of V. I'm going to find the dimension of W. So I want the dimension of the domain. I want the dimension of the vector space W, the codomain. And then we're going to find the rank of T. That's one of the things that it asked us to find, was rank of T. And we're going to find the nullity of T. That was another thing it wanted us to find. And then we need to determine whether or not this is 1-to-1 and or onto. So is this 1-to-1? And is this onto? That's a question mark. And is this onto? Question mark. Okay. So let's run through this. Like I said, this kind of covers a lot of what we've talked about, which is great. So remember that the dimension of V is simply n, right? We're mapping from n to m, so the dimension of V is n. So we can just literally count the number of columns in each of our matrices. So A has 3, B has 2, C has 3, D has 3. So it's just 3, 2, 3, 3. And then same with W, right? It's just going to be the number of rows, because that's what we're mapping to. So 3, 3, 2, 3. 3, 3, 2, 3. All right. Rank of T. Remember, rank is the dimension of the range. So in this case, we're looking at basically how many rows have leading ones in it. And so A has 3, B has 2, C has 2, and D has 2 because the last row is zeros. And then the nullity, that is the dimension of the kernel. And in this case, then we're looking at how many columns do not have a leading 1. So the first one, all the columns have a leading 1. So there's 0. B has 0. C has 1, the last column. And D has 1, also the last column. Okay. Obviously, we could also use the formulas, right? We could do the n minus rank. So in other words, in this case, so n was the dimension of V, m is the dimension of W. So if we did this correctly, the rank plus the nullity should give us n. 3 plus 0 is 3, 2 plus 0 is 2, 1 plus 2 is 3, and 1 plus 2 is 3 again. So those last two columns should give us that first column, the sum. All right, and then finally, is it 1-to-1 or not? So here we're asking, is the kernel of T equal to 0? Well, obviously for A and B, the answer is yes. For C and D, the answer is no. And then is it onto? And here we're asking, is the rank of T equal to the dimension of W? That's why I kind of threw that in earlier, the dimension of W. So in this case, we're looking at the rank and the dimension. So A is, B is not, C is, and D is not. So we've got yes, no, yes, no. All right. Now, obviously, then, when we think about that last theorem where it said that, it's both 1-to-1 and onto, remember that both have to be of the same dimension. So in this case, the only two that could have been yes to both 1-to-1 and onto were A and D. A obviously is both 1-to-1 and onto. D is not. It's neither. B and C could not have been two yeses because they didn't have the same dimensions in both V and W. So just kind of a little reminder there. So like I said, I really like that activity, that example, because I think it pulls together so much of what we talked about and makes some really good connections. A lot in this lesson, long lesson. I apologize for that, but a lot in there, good stuff. And make sure that you're doing the work in the book to get some practice. Reach out if you have any questions. Otherwise, I'll see you in the next lesson.